Anybody here ship 0 defects? No? Once? Sometimes. Yeah, that's the way it seems to work sometimes. So a little bit about RJG. We make our customers more competitive by giving them the ability to ship only good parts. Part of that is, and part of this presentation is going to be, you have to minimize your risk. If you're going to do that, you have to minimize your risk. In other words, you can't make as many bad parts. That's step number one. You have to optimize your process. We make our customers competitive by using sensor-based technology to determine what systems are functioning correctly. And I'll go into this in a little bit more detail in the next couple slides. Determine what process setups are correct. Determine what processes are stable and in control. Those are the things that we need to start with. We have the ability, the equipment, and the technology to contain all suspect and abnormal parts. Develop automated process control solutions from the plastics point of view. How many of you guys have been through our training? Anybody out here been through our training? So some of this terminology you totally understand. So desired future state. What do we want to see? As processors, what do we want to see? We want to see that all good parts are being made. We don't want to see bad parts being thrown into a box, or even worse, thrown into a box and shipped to the customer. That's worse. We know they're good without manually inspecting them. That's pretty important. That's labor. I mean, how many of you guys can relate to a situation where products have gone elsewhere because of labor cost? I can. I certainly can. All scheduled machines are running, and you know they're running. They're running to the correct setup. The machines are capable. You have capable molds, standard method of molding. You have a standard methodology for building your process. And problems find you. So the end of all this is, we don't want to send any bad parts to our customer. So the question here, is it possible to run an injection molding process long-term without producing bad parts? I've been doing this, as a lot of you have, for many years, and I say no. I say you're going to make bad parts. There's abnormal variation. Somebody's not going to turn a thermolator on, a chiller on. You don't purge the machine out properly before you start the process. You're going to make bad parts. Normal variation, material viscosity, and I've got some data here that kind of supports this, but also checkering repeatability. So we have to plan for success. We have to minimize the possibility of producing a reject. Material selection is important. Mold design, machine selection, and process optimization. I can't tell you, in my career, I think I've been doing this about 28 years, I can't tell you how many times I've fought problems because something wasn't right. Wasn't right in the mold design, there wasn't enough draft, radius, something, too much texture. Machine selection is a big one. We don't choose a machine that will provide enough pressure to pack the part. We can't fill it fast enough. The volumetric flow rate is too low on the machine. All these things are you have to take consideration of all these items. Process optimization. A short story on process optimization, or a methodology that everyone does things for the exact same way for the exact same reason. I was actually doing a demo of one of our systems, and it's interesting how many ways you can fix one particular problem. So the story goes, the very quick version of this story is, we had a problem, very tight tolerance part, very small processing window. And we had our eDart system set up on it, so we could see everything that happened throughout the night. And we asked the process technicians to make notes. Anytime they made a process change, please make a note on our summary graph. So about 3 o'clock in the afternoon, we had a sink in the part. So process technician came up and moved the transfer position. Okay, he packed out the sink. About 3 hours later, the part was sticking in the cavity. It was overpacking. So another process technician, different process tech, came over and reduced the shot size. He did several things. Reduced the hole pressure, a couple of different things, you know. We call it the molder's dance. Did a couple things. long story short, this happened 3 or 4 times back and forth, overpacking the part, underpacking the part. As it turned out, it was a material-related issue, but there was 5 different process changes made to fix that process. So it's very important to understand the process and how to optimize the process. Everyone doing the same thing for the same reasons. So material selection, molecular weight, tensile and compressive strength is important. When we start a process in the beginning, we start to build a tool, that's the first consideration that we think about. What material are we going to use? Hopefully, because that's going to predict and help us in designing our tool. This is very, very important. Another big problem that I've fought in my molding career is people that have designed a part for one material and one shrink data, one shrink factor, and try to run other materials. Very difficult, and it will absolutely take an optimized process and narrow everything down to the point where it's almost unmanageable. So this is our summary data. This is summary data. It's data over time, plotted over time. We call it our summary graph, and this shows material variation. Material variation is going to happen. So we have to understand how to optimize both our mold, our machine, everything, so that we can absorb this expected variation. Part and mold design is also a consideration. The melt delivery system, the runner design, is very important, very critical. Sufficient draft and radius, uniform wall thickness, all these things most of you guys have heard before. Proper considerations for additions and subtractions, gate locations, texturing, and venting. So optimizing the tool is also important. Machine selection, injection velocity. We talked about this in the beginning. If you pick a machine that won't go fast enough, won't provide enough pressure, you're not using the proper ratio of shot capacity, or it's too small or too big in clamping, it can also create these issues. Process optimization. Those of you that have taken our training, you know that this is what we focus on. We focus on the 4 plastic variables: the melt temperature, the fill speed or the volumetric flow rate, pressurization, cooling rate, and time. That's what most of our training is about. That's what we focus on. That's how we process. That's how we roll. So all of this leads into, I want to talk just a little bit about RJDS training. Everything that we've talked about now, we cover in our training. Machine selection, a little bit about material, quite a lot about the process. All of this stuff is part of the package deal that RJG offers, training and equipment. I know this is 0 defects, but this is really important. You've got to plan for that success. You can take a mold. How many of you guys get transfer tools? You didn't design it. You're living with somebody else's mistakes, right? It happens. We've all been there. There's still a solution. Some of our training that's available: essential systematic molding. Systematic molding is just kind of what I touched on earlier. Everyone being on the same page and understanding this, what part of the process affects what, so that the right process adjustments are made. Systematic molding, Master Molder 1, Master Molder 2. These are much more in-depth trainings. Master Molder 2 now has to do quite a bit with our EDART system. We've incorporated that into that training quite a lot. And then successful strategies for new tool launch is more geared towards design engineers, people that are involved in designing tools. But again, the RJG training focus is validate machine and tool capabilities. We train on how to do that. How do you validate, is this machine capable? Can it do what you need it to do for this process? Build and document a robust decoupled process and process documentation. So how to build it, and the beauty of this is, and I've, as a customer of RJG for years, we incorporated this, and it's very interesting to watch what happens when people start doing things the same way. It changes a lot. It will change your business dramatically. Build and document processes, decouple processes, and documentation. Documentation, if you document properly those 4 plastic variables, how hot was the melt temperature when it entered the tool? What was the flow rate when it entered the tool? What did you pressurize it to in the tool? What was your pressure distribution? And how quickly did you get the heat out of it? If you document that well, that is your process, no matter what machine you run in. Then you just got to figure out, is the next machine capable? Can it do this? Can it do the same thing? And last of all, trouble kill problems if they develop, when they develop. They're going to develop, right? That's what we do. It's just the nature of our business. I use the word trouble kill because how many of you guys solve the same problems every other week? That's troubleshooting, if you will, but that's not trouble killing. I forget where I was at, and it's not important, but we're having a conversation about a problem that kept reoccurring. And somebody said, well, get Jim. He fixed that last week. No, Jim didn't fix that last week because he's got to go look at it again. That's not fixed. So really need to concentrate on trouble killing. Systematic molding training, this is what it goes through. And if I'm not going to spend a lot of time here, but if there's any interest, see some of the guys after the presentation, and they'll fill you in a lot more on what each one of these training programs consist of. So we have the systematic, the master molder certification, but I do think this slide is important. So systematic molding, as we define it, making operational decisions based on data and analysis, as opposed to only intuition, opinions, and politics to achieve optimal results. Now, you guys have been in the business a while. You know how this works. Everybody's got an opinion about what's wrong with a part, but if you're using data, if you're using true data, there are no opinions. It's factual. Using monitoring, containment, and control to achieve a level of quality always exceeding the customer's expectation. So what is the cost of making a reject? Well, the obvious cost, right? Material, the cost of the material, the machine cost itself, labor cost to reproduce the part. You got to make it again. Even if you grind it up and use it as regrind, you still got to make it again. And cost of failure in the field, which can be huge. Any of you guys mold for automotive or medical? You don't want that to happen, right? That's not an option. What's the cost of shipping a reject to your customer? I say priceless for your competitors. The competitors obviously want you to send some bad parts to your customer. But customer satisfaction is going to be, there's going to be some pain there. Corrective action request. How many of you guys have had to go through the pain of 8Ds and all this kind of stuff that your customer wants you to do because you sent them a bad part? That's very time-consuming, labor-intensive. And 100% sorting. If you're in the automotive industry and you send a bad part, at least in my experience in the past, you get one opportunity. The second opportunity, you 100% sort everything you make for a period of time. And if you do it again, you hire an outside source to do 200% inspections. So that's very, very very labor intensive. So back to that tool that you inherited. You've got someone else's problems. Somebody decided that you can mold this part cheaper than they could, so they moved the tool to you, and it has inherent problems. One of the things that we can do is instrument the tool. Even though things aren't perfect, it's not going to be perfect. You had no control over the design. We can monitor each of the cavities with pressure and or temperature and make good decisions based on data before the mold opens on whether this part is good or this part is bad. So that's what I want to talk about a little bit now. Selecting the sensor placement. So we want to look at a few different things. One, we want to put a sensor in the hydraulic system somewhere. That with a little bit of math, we can calculate material viscosities. Material viscosities do change, and we want to know when that material gets harder to push or easier to push. It has a big effect on our part. So we'll use some machine-based data to give us that information. We also want to put sensors in the cavity, because sensors in the cavity, that's the rest of the story. Basically, that's what you're selling. What's happening in the cavity is what's going to your customer. The gate, the end of fill, we're going to call it the end of fill. It's the last place to see plastic in the cavity where your short shot would be if you were to make a short shot. Put a sensor there. We're also going to put one for this conversation in the highest pressure area of the part, the gate end of the part. What we're going to do with those, end of cavity, we're going to look at non-fills. Obviously, short shots are going to be real easy to see. If we don't see pressure there, we have a short shot. SPC data can be taken from there, and we'll get into that just a little bit more. And automatic part separation. We can use that to separate bad parts. Gate end of cavity, pressure drop across the cavity. Degree of packing, hold time optimization. And we can also use that as a control point. If the viscosity changes in the process, what happens if the material gets harder to push? We don't put as much material into the cavity. We don't pack it out as much. The part is smaller. If we use that pressure to control the process, we minimize the effect that variation has on the part. That part doesn't change nearly as much when the viscosity changes. So a typical cycle graph. How many of you guys have seen typical our EDART data before? Okay, good, good. So what we're looking at here is time, and in this axis is pressure. The red curve that you're looking at is hydraulic pressure in this situation. It's measured in plastic pressure, but it's taken right off the hydraulic circuitry of the machine. And the spike that you see there, that is the amount of pressure that it takes to fill the tool hydraulically. That's how much hydraulic pressure is being applied to push plastic into the tool to fill it. Remember I said we could look at viscosity and see if material viscosity changes? We call this the effective viscosity. If it takes more pressure at this point, in other words, we see this go up and then transfer, we know that the material got harder to push. We can calculate the percent of change and tell you at what percent of change your viscosity was. Same thing if it gets lower. If it takes less pressure to push X amount of plastic in the tool, we know the material got easier to push. That's a huge step in the right direction. That's really good data to have. So we fill the mold, we transfer, and we go to a set pack and hold pressure. Again, this is still a machine curve. Inside the tool, we have our post gate sensor, which is our high pressure area, our end of cavity sensor, which is our low pressure area. We can see from this data, cavity fill time. This is when injection started, this is when the cavity's full. When the cavity's full, you can start to pack it. The rate at which we pack is right here. The slope of that curve is the pack rate. How much plastic we packed in the tool is the peak pressure. If we put more molecules in that tool, pressure goes up, part gets bigger. Put less molecules in the tool, plastic molecules, pressure goes down, parts get smaller. Pretty simple, really. After we pack the tool, what happens to plastic? We heat plastic up, it expands, we pack it into the tool, then what happens? It shrinks. As plastic shrinks, it's pulling away from that sensor at a given rate. We call it, that's the same as a shrink rate. And the decay of this cavity pressure curve right here determines shrink rate. It's the same as shrink rate. So here we can see cavity fill time, cavity pack rate, peak pack pressure, which is the peak pack pressure at the post gate and at the end of fill. So both ends of the part, and we can see how they cool. We can see the shrink rate. So we can kind of see it all right here. A little bit about the sensor installation. Now I've got what we call an indirect installation here. Ejector backup plate, ejector pin plate. This is counterboard, and we've relieved an area for the transducer sensor wire. This is not a press fit or anything. These sensors just fit right down in there, bolted together. This kind of shows a cutaway of the sensor underneath an ejector pin. The way it works, the ejector pin sees the pressure, and it transmits the force down to the sensor. EDART reads the data. So we have one here at post gate. We have one at end of fill. There's this. So, Mel, have you ever seen that part? This is a part that we worked on and for dimensional data. This is an antenna carrier for a mobile phone part. Very difficult. On the back side of this part, I got a picture of the wrong side of the part, but on the back side there's a boss-to-boss dimension. Very difficult to maintain that boss-to-boss dimension, and very critical. And this is kind of how this automated part containment thing works. Cavity pressure, most times, with most materials, there's a direct correlation with the pressure in the cavity and pressure distribution and part dimension. So this is kind of an indication of that right here. This will show. This is that boss-to-boss dimension. So the end of cavity peak pressure is the light blue curve, the light blue line, and the dark blue is the boss-to-boss dimension. So you can see when the end of cavity peak pressure went down, so did that center-to-center dimension on the boss. And you can kind of see that it trends very well right there. That's like 17 shots in a row. And now I've got it kind of, this is 1 inch 252, 1 inch 247. So we're not looking at a whole lot, but you can see that it trends, and you can set alarms based on that. Once you find out what your critical part dimensions are and find out what correlates with it. Now we have a tool on the EDART system that does some very simple single variable correlation. So we can find this relatively easy. And if you can't find it with the simple method, you can always do a DOE. Everybody loves DOEs, right? Once you find out what that is, this is, again, the summary graph on the eDart screen, we can set up alarm limits. And based on these alarm limits, when we have one that goes out, of spec, we could have something in this situation. There's a 6-axis robot, and the parts were taken out of the machine, and we called everything suspect. We didn't call it a reject. So what we did is actually pack the part out here so that an operator could slide this out and take a look at it and confirm. So that's how that's the capabilities of running zero defects. No, shipping zero defects. Yes, it is a possibility. I have several customers. I'm from the South region, Texas, New Mexico, Oklahoma. I have several customers down there that have shipped millions of parts at this point with no defects to their customers.